Alright everyone, so I want to provide you a little bit of background here. First of all, I want to point out that in the book, a lot of these things are discussed, so please use that as another reference. It's chapter 10, I believe, in the book. And then you have some other places. If you look in the index, for instance, if you want to know about degrees of freedom, there are some good descriptions that Andy Field provides in the book about degrees of freedom, about z-scores and t-scores and that kind of thing, and also step-by-step instructions on how to do these things in SPSS. So please make good use of the textbook. I think you will find it very useful for you, and along with the videos that I am providing to you. Alright, so let's pick up a little bit where we left off last time before we jump into thinking about a t-test. So if you remember this image from the end of the video last time around, we were looking at the 1,000 largest cities, as of 2008. So if you remember what we did here, the top plot is the sample means in terms of the actual population values, and then the bottom dot plot represents the sample means in terms of z-scores. And if you need a video about z-scores, let me know. I can provide a short video about how z-scores work, because they're pretty important here. And remember, we were talking about how this data point out here where the red line is beyond 3 standard deviations away. That's what a z-score tells you, is how many standard deviations away something is. But here's the problem. A z-score, in order to turn that into a test, the assumption is that you know what the population standard deviation is. And if we knew that, we probably would also know the mean already, and so it kind of defeats the purpose of the test to begin with. Why would we have a sample from a population, and if we know the standard deviation of the population, we probably already know the mean of the population, so what's the purpose? Alright, same thing here. So if we are thinking about these roller coasters as a sample of some larger population, perhaps thinking about the roller coasters he would have made that weren't in this data set. So if you think about it like that, we don't know what that is, so we can't use a z-test. And instead we use something called a t-test. And a t-distribution was actually invented because there was this guy who was trying to create samples of beer. He had to test them, and he knew that he couldn't test enough of the same kind of beer over and over again in order to use a z-test, because the sample size would have to be too high. So instead, he created what's called the t-test, which allowed him to have a small sample and be able to test three samples from a beer instead of, say, 30 or 40. A t-score is exactly the same thing as a z-score, but the distribution is different because every distribution looks a little bit different based on the sample size. You can simply type in t-distribution by sample size into Google Images, and you'll see lots of great plots about this. There's also some description of this in your book. So what I want to go to is the t-test. So first, it's really important to recognize that in this distribution, when we think about the z-score, for instance, on the bottom being more than 3 standard deviations away, that has a special name, because this is not the standard deviation of the sample, it's the standard deviation of all the possible sample means of the sample size that we're collecting, which in this case was 100, right? So sample sizes of 100 have means that would look like this if we were to repeatedly pull samples from the population over and over thousands of times. The standard deviation of that distribution is called the standard error. It doesn't mean that there's error not meaning a mistake, but the standard deviation of the sample size is referred to as the standard error because it is how much things could deviate from the truth. Because remember, this are samples of things that all are supposedly telling us something about the population that has a specific mean. So it's giving us an idea of how things vary from that true center wherever it might exist. And we use it in order to help us understand how far away our sample is from what the mean is expected to be, and whether or not what we have found is something different. Or in the case of two samples, we're trying to understand whether or not they are far enough apart from one another as samples so that the distribution here, the standard error, would tell us that they are too far apart, and more than likely we didn't get these two samples by chance. So the standard error helps us understand that, and the p-value is calculated from the standard error and the t-score. Okay? So if we now go... one other point that I wanted to make about degrees of freedom. So imagine if you had a mean of 10 things, and let's say the mean was 100. If you knew all of those things except for one of them, could you figure out what the last data point is if you knew the mean and how many things there were? If I told you the mean is 100 and there was 10 things that added up to that mean, and I gave you 9 of the 10 values, could you figure out what the 10th one is? The answer to that question is yes. But if I gave you 8 things, which means there's 2 values you didn't know, would you be able to know the exact values of those 2 things? And in that case, you would know what the sum of those 2 things is, but you wouldn't know the exact precise value of those 2 things. That is the idea of degrees of freedom. So if you have one sample, the degrees of freedom is 1 less than the sample size, because that is the one thing that can vary. There's one value that could be missing that you could still figure out what it is, right? And if you have 2 samples, in the case of what we're doing for the roller coaster data, then there's 1 degree of freedom for each sample, which means there's 2 degrees of freedom. That's what that degrees of freedom means, and actually it gets a lot more complicated than that as you change into different types of tests, and you'll see some other things that are different once you actually run the test. There are also several assumptions for the test, which you can also find in your book. One of them is that the data has to be normally distributed. The other one is that the data has to be equal variances. And in general, you want sample sizes to be fairly high, and the 2 groups have to be independent of one another. Otherwise, there's a special test called a paired t-test. That would be used in the case of a pre- and post-test, where each person is in both samples, therefore they're not independent of one another. In our case, though, the custom versus non-custom roller coasters, we do not have this issue. We do have independent samples. All right, so let's go to SPSS. So to run a statistical test, what we're doing to answer the research question is we're comparing the means of the 2 groups. So we go to compare means, and you'll see some different options. 1 sample t-test. That's not what we want. We have 2 samples, an independent samples t-test, a paired samples t-test, and a one-way ANOVA. These all compare means. The paired samples t-test is for things that are like a pre-post kind of context, in education at least. But we want the independent samples t-test. We're trying to decide if these 2 different types of roller coasters differ on the mean of some other value. So I'm going to run this. Let me reset this. On a different variable than you're doing for your homework, but let's say we want to tell if they're different in intensity. So we put intensity as the test variable, and it has to be scaled. And then we use the custom design variable as the grouping variable. And notice these question marks here, and then it says define groups. So click on that, and we know that group 1, that has a 1, that is the group that is the custom designed roller coasters, and group 2 will be 0, the non-custom. You could reverse these, it doesn't matter, just know which one is a 0 and which one is a 1. The only difference is that when it subtracts the 2 means, it will subtract group 1 minus group 2. So in this case, it'll be the mean of the custom divided by, or minus the mean of the non-custom roller coasters. So the sign of that will tell you which group is bigger. You'll have to just pay attention to that. All right. And someone in the Discord had asked about bootstrapping. Bootstrapping is a method of randomly selecting from the sample itself over and over again, which helps avoid assumptions. We're not going to get into that in this course. I'm open to a conversation about that if you want to talk more about that. But right now, don't worry about it. Under options, you'll see an option for a confidence interval percentage, which is also related to a cut point. But at this point, I want you to be thinking about the p-value, not about that. So we're going to leave that as 95%. Okay, I'm going to click OK. It's going to open this up. And we see here the group sizes 99 and 43. We know that those are the sizes. Nothing is missing. See, the means are about 7, or 6.7, I mean, and 7.1. So at this point, I'm looking at that thinking, I don't know that there's going to be a difference, but here's an issue. Look at the difference in these standard deviations here. 4 and 1. About. That difference is really big, which means that the video game default roller coasters were very much more similar to one another in terms of intensity, and the custom created coaster group is very different from one another. And if you think back to some other conversations on Discord and other assignments, you'll remember that it seems like there is a smaller group of roller coasters whose speed is a lot smaller than the others. And if speed is related to intensity, that makes sense. If there's like a little kid park, for instance, maybe the video game default didn't have that little kid park. So that creates this bigger standard deviation, perhaps. We're looking at intensity, though, not speed at this point. But those being different gives us an idea that probably we can expect that the variances are not equal, which means we're violating an assumption of running a t-test. Further, when the t-test is run, the standard deviation is taken into account for the mean. So just because these means are not very much different from one another, because the standard deviations are very different from one another, there's still a possibility of seeing a difference. So if you look at the p-value here, you'll see two different p-values. One of them, both of them are big. So ultimately, it doesn't matter which of these rows we choose. Equal variance is assumed or not assumed. But the Levine's test is telling us with this high p-value, 0.462, is saying that these means are not, or that the standard deviations can be assumed to be the same, which actually doesn't make a whole lot of sense, but my guess is it's related to these sample sizes. So they are not different enough to matter. If the significance was 0 here, or less than 0.05, then we would use the bottom row. But as you can see, it doesn't matter. I want to point out that the degrees of freedom are 140, and if you sum 99 and 43, you get 142, and subtract 2, you get 140. That's where that comes from. Equal variance is not assumed. The bottom row, the degrees of freedom are calculated, and they are adjusted based on that difference. So don't worry about how it's calculated, just know that it's something that has to be reported with it. So the significance here is very so the p-value is high, which means about 52% of the time, if we collected random samples of size 99 and 43 for these two different types of roller coasters, we would see a difference between 6.7 and 7.1. Which is only a difference of 0.42. So it's not much of a difference, and there's not much to worry about there. You can see the standard error is 0.64. So that is a pretty low standard error, which means that these values are in the population. If you're considering pulling random samples from it, they're going to be fairly close to one another. Much different than these standard deviations. All right, so that is how you would report that. So you might say when we're thinking about intensity, the difference in the means is only 0.42, with the default coasters having a slightly higher intensity, but that difference is not statistically significant, with a t-score of negative 0.65, degrees of freedom of 140, and a p-value equal to 0.517. And you could also report the standard error if you wanted to. I would do so parenthetically. All right. So I hope this video is helping you understand t-test a little bit. Please read your book. Please post things in Discord. Let me know what other things you're needing help understanding, and I will post other videos. I will put things on hold if we need to make sure that you're getting what you need here. So I apologize for not getting this up sooner. I have been traveling, as you know. I am still traveling, and I should be back in Cruces on late Tuesday sometime. All right, so I hope you get what you need out of this. Let me know what else I can do to help you. All right. And I will see you in Discord.